Less than 3 light hours from the supermassive black hole at the center of our galaxy, a star the size of our Sun is whipping around at over 7,000 kilometers per second, and its orbit is being used to check whether Einstein was right, down to a few parts in 1,000. Black holes are not just destructive monsters, they are precision laboratories for gravity. Near them, space-time is pushed to its limits. Gravity is so intense that the usual weak field approximations we use near Earth completely break down. That makes black holes the perfect place to test general relativity. Einstein's theory that says gravity isn't a force in the traditional sense, but the curvature of space-time itself, shaped by mass and energy. To see how extreme this gets, start with light. In Newton's universe, light has no mass, so gravity shouldn't bend it at all. But in Einstein's picture, light follows the straightest possible paths through curved space-time, called geodesics. Near a black hole, these geodesics twist so violently that light can loop around it, forming Einstein rings and multiple images of the same background object. In the most extreme cases, photons can orbit the black hole on nearly circular paths, at the so-called photon sphere, at 1.5 times the Schwarzschild radius, the radius of the event horizon for a non-rotating black hole. Astronomers have actually watched this light bending happen. When a black hole passes in front of a distant star or quasar, its gravity acts as a gravitational lens, magnifying and distorting the background light. By measuring exactly how much the light is bent, we can test Einstein's prediction for the deflection angle, originally confirmed near the Sun during the 1919 eclipse, and now probed in far stronger gravity near black holes billions of times more massive. So far, every precise measurement of these lenses agrees with the curvature predicted by general relativity. But light isn't the only clock we can use. Time itself ticks differently near a black hole. According to general relativity, the closer you are to a massive object, the more slowly time passes compared with a distant observer. This gravitational time dilation is tiny at Earth's surface, but near an event horizon it becomes dramatic. To someone far away, a clock falling toward a black hole appears to slow, its signals redshifted to longer wavelengths, seemingly freezing at the edge. We can't drop literal clocks into the black hole at the center of the Milky Way, but we have something almost as good: stars in close orbit around it. One of them, called S2, swings in to about 120 astronomical units from the central black hole, roughly 3 times the distance from the Sun to Pluto, and then races back out on a 16-year orbit. At closest approach, its speed reaches about 2.7% of the speed of light. During this pericenter passage, both Einstein's gravity and special relativistic effects become measurable. By tracking S2's motion over decades with infrared telescopes and adaptive optics, observatories like the Very Large Telescope in Chile have watched its spectral lines, the fingerprints of elements in its atmosphere, shift toward red at closest approach. Part of that shift is just the Doppler effect from its rapid motion, but an extra component matches exactly the gravitational redshift predicted by general relativity. Light climbing out of a deeper gravitational well loses energy, stretching to longer wavelengths. On top of that, S2's orbit itself is not a perfect ellipse. Its point of closest approach slowly precesses, rotating in space, in the same way that Mercury's orbit does around the Sun, but here magnified by the extreme curvature near a 4 million solar mass black hole. All of these effects, bending of light, slowing of time, twisting of orbits, are places where Einstein's equations could, in principle, fail. Yet every time we push them closer to the edge of an event horizon, they still hold, which raises a deeper question. If general relativity passes all these tests near black holes, where, if anywhere, does it finally break?